Here's a very quick thermodynamics question which can be solved in just one page or just a couple of lines, I mean. And this is the kind of question that you would see as probably high school student or as a first year undergraduate if you're doing something like engineering. So here's what we know. We're dealing with a nitrogen gas, right? So we have N2, and we know that this nitrogen is receiving heat in an isobaric process. This is this part of the question. And the amount of work done by the gas is equal to 2 joules. And we have to find how much heat does the gas receive to be able to perform this amount of work. And what I would do, first of all, is I would just write down the formula for the first law as it applies to closed systems. And then I would look at each element individually, right? So, of course, we have delta U, which is N, and then we have CV times delta T. So I'm using the molar form in this problem. And then we have the work. Now, keep in mind the work is process dependent. So we know the process, it's isobaric. So the work is just pressure times the change in volume, which is the same as N times RU, that's the universal gas constant, remember, because we're using moles, times delta T. So if we add those up, if we add delta U and W, we're going to get Q. In other words, we get Q as NCV times delta T plus NRU times delta T. And by the way, you can do this with mass as well if you want. So I can convert those N's to M's as long as my RU becomes the specific gas constant. But I'm doing it with moles because the book I have this from is using moles. So now we can actually factorize N and delta T. So we're left with CV plus RU times N delta T. And of course, we know that CV plus RU is just CP. It's the specific heat at constant pressure. So this is CP, or I should say N times CP times delta T. And you could get this formula from like a formula book if you want. Okay, so we could have actually started the problem from here, but I just wanted to do this quick derivation as a reminder, I guess. So we have two things. We have heat as N Cp times delta T, and we also know the work, right? So the work is Nr delta T, and the work is given the letter A, which is 2 joules, right? So what I'll do then is I will take this expression for Q for heat, and I'm gonna write it in terms of this, and here's how we do that. We know Cp as gamma over gamma minus 1 times Ru. Okay, so this, remember, this used to be Cp times delta T. So the heat is, so what I'll do now is I'll take this gamma over gamma minus 1 and I'll bring it, just move it a bit to the left. So this is gamma over gamma minus 1 and Ru delta T, which is gamma over gamma minus 1, and Ru delta T, which, by the way, this should be Ru as well. This is, of course, the work, or A, as they call it in this question. So that's it. This is basically, if you want, the heat as a fraction of work, but now we also have to find gamma. Gamma, you can find it from tables, but I'm a big fan of deriving things from scratch, so I'm going to use the degrees of freedom approach. So we know that gamma is I plus 2 over I, where I represents the number of degrees of freedom of the gas molecules, So I'm not going to go into detail, but if the gas is monoatomic, right? So if the molecule is just made of one atom, for example, if you're dealing with helium, right, this would have an I of 3, which corresponds to the fact that the molecule can move along X, Y, and Z. But if we're dealing with N2 with nitrogen, then we have 5 degrees of freedom. So this can move along X, Y, Z, but it can also rotate. And this is what we're going to use, and then gamma becomes just I plus 2 over I. So that's going to be 7 over 5, which I think it's 1.4, which is the same gamma as for air, if you think about it. So if we take this and if we put it here, we should get our value of Q. So Q becomes equal to, so gamma is 7 over 5, and gamma minus 1 is 2 over 5, and A is 2 joules, so times 2. Right, the 5 and the 5 go away, so we have 7 over 2 times 2, and the answer is 7 joules. So if we give this gas 7 joules of heat, 2 of those joules are going to help the gas to work, and the rest of them, the 5 joules, are going to increase the internal energy of the gas. And in this way, we can make sure that the first law of thermodynamics will be respected. And that's the end of the question.